So our maxima and minima problems, or optimization problems. Basically, we're getting a word problem. We want to turn it into maths so we can use our calculus to go and find the optimal solution. So we'll usually reduce our problem to a set of equations. Normally there'll be two. Yeah, okay, sometimes it's different to that, but usually for these problems we're going to find two. Now, one of those, it'll be obvious what the equation is, or what you have to work out anyway, because it'll say what is the maximum or what is the minimum of this. So that's the function you've got to come up with. You've got to come up with an equation for that particular quantity. Then inside the problem then, there'll be some other information, some amount of material or some cost or something like that, but they'll give you some information and then you create a second equation out of that. So then you rewrite it. So very similar to simultaneous equations, but we rewrite the equation we're trying to minimise and maximise, so it's only got one variable to look at, thus turning it into a two-dimensional problem. And then we go and use our calculus and go and find what is that maximum, what is that minimum. So okay, let's have a look at a very typical problem. I'm sure you've had this problem yourself, where you've got yourself a 36 metre long rope. You go, well, excellent, look at this rope. I'd rather have two pieces. So I'm going to cut it into two pieces, and when I bend the first bit of rope, I'm going to make a nice square. But the second one, I'll make a rectangle. See, maybe we're trying to trap ants inside this rope. I don't know. We want to find, where do we cut it basically? So what's the length of the square going to be, so that the area that I'll capture with these two shapes will be a maximum. I want the biggest possible area that I can. So that's the problem we're presented with. Diagrams are always good to try and see what it is that I'm trying to do. So I'm going to have a square, I'm going to have a rectangle. So let's turn this into algebra. I'll give the square some dimensions, S for side of square. Now we were told one of the sides of the rectangle was the same, so it'll be S, and I'll call the other side R for rectangle. So we have our dimensions there. I can now come up with my first equation. I'm trying to maximise the sum of the two areas. So the area will be S squared plus RS. Unfortunately now, I've got three pronumerals I'm dealing with, and I want to turn this into a two-dimensional problem. So I need something else, the other piece of concrete information that they've given me. And that's right at the start of the problem. We know the rope's 36 metres in length, but remember, we're using this rope to form the square and the rectangle. So it's going to be the same as the perimeter of these two shapes. So 6S plus 2R must equal 36. I now want to eliminate one of these. The smart one to eliminate would be R, because that's going to be a lot easier than trying to get rid of the S. So let's make R the subject. In the second one, I'm going to sub in 18 minus 3S and substitute that into 1. Excellent. I mean, I've got to expand it out and what have you, but I've got what I want. I've got a two-dimensional problem now. From there, it's now calculus. If I wanted to, I could draw, well, it's a parabola, isn't it? I could draw that parabola and look at it and say, well, what's the, we're trying to maximise. So, yeah, well, that makes sense. It's a concave down parabola, you'll notice. So we don't necessarily need to use calculus from this point. We could use what we know about parabolas, because it turned out to be a quadratic. We're looking for the vertex. But we'll use calculus, because that's what we're doing today, isn't it? So let's find our derivatives. Let's find our tools that we're going to use. First derivative, second derivative. That's all I'm going to need for this problem. I'm trying to locate the maximum. So I've got to find those stationary points first. In this case, it'll be dAds I'm finding. So when's dAds equal to 0? Solving my little question there, I get 9 on 2 for the side. Let's confirm. I mean, logically, yes, it's an upside down parabola. Logically, it's going to be a maximum. But let's just make sure it is. Second derivative is actually a constant -4. So it's less than 0. So yeah. So when the length of the square is 9 on 2, 4.5 metres, the area is going to be a maximum. We've solved our problem. But the interesting thing about that is if the length of the square is 4.5 metres, what does that tell us about the rectangle? It's also a square. Because remember, we had, where was it? Here it is. The length of the rectangle is going to be 18 minus 3S. If you substitute in what we've found, it'll also be a square. And in optimization problems, this happens a lot, that the optimal solution is when the shape is a perfect shape and the perfect rectangle is a square and things like that. It happens a lot. Okay, let's do another one. We're going to have a bucket. And our bucket, just to make life a bit easier for our question, is just going to be a cylinder. So it's not one of those tapered buckets that go, it's going to be just a straight cylinder. It's going to hold the largest possible volume of liquid that we can. But we've only got 12 pi units squared of material. Now again, we're simplifying the problem here because we're imagining that we can use every piece of material. Now in reality, as I say, this would be when we start going to bigger problems in higher dimensions, because we'd have wastage. And so we might have another formula for wastage, and we want to minimise that and things like that. But we're assuming we can use every single piece of material, yeah? We want to find the height, the radius and volume of our bucket. All right, there's a picture of our bucket. That's a cylinder, so let's call it radius r, height h. Volume, that's what we're trying to maximise, pi r squared h, of course, for a cylinder. Surface area, formula for a surface area is, well, now if we use 2 pi r h plus 2 pi r squared, we're going to have a problem, because we won't be able to pour any liquid into the bucket. So for our one, it'll be pi r squared plus 2 pi r h, because we want a bottom on the bucket. We don't want the water to flow out, but we need it to get in. So 12 pi will be pi r squared. Wasn't it fortunate that our measurements turned out to be a multiple of pi, because now pi will cancel in our equation. Oh, that was lucky. Okay, going to make h the subject for this one. And we end up with 12 minus r squared over 2r. Let's sub it into our volume formula. So there it is. Well, r will cancel with the r squared. We have 6 pi r minus a half pi r cubed. We'll get our formula. It's a cubic this time. So one of the stationary points, logically, if it's a cubic, one will be a minimum, one will be a maximum. But let's differentiate. First derivative, second derivative. Stationary points will occur when VDR is equal to 0. So I want to solve this little quadratic. So r equals plus or minus 2. Now, I'm not going to test both of those. There's a logical one to pick and an illogical one to pick.
A negative
radius. I'm not going to build a bucket with a radius of negative 2. So the logical one to choose is positive 2. So sub in positive 2, and yes, I get a negative number, negative 6 pi. That's less than 0. So yes, indeed, when the radius is 2, the volume is going to be a maximum. So we've found the optimal solution. Now, we go back and read the question carefully, make sure we know exactly what it is. What we're trying to find, what was it they asked for? Was the radius, the height they asked for? Did they want the volume as well? Okay, so we're finding all of it. So when r equals 2, h, we've created a formula for that earlier, also equals 2. There we go. There's that perfection coming in again. And the volume, therefore, pi r squared h turns out to be 8 pi. 8 pi. Don't just leave those answers hanging around. Conclude it, right? I've solved this problem. The maximum volume is going to be 8 pi units cubed, and it's going to happen when the radius and the height are both 2 units. So it's a rather strange bucket when you think about it. It's short and fat. It's like, ooh, rather than what we traditionally see. Alrighty. Well, we're going to have a lot of fun. 4H and 4I solving some of these optimization problems.